Swayam Prabha. Digital India. Educated India.
We were discussing in the last few classes the evaluation of stress intensity factors for variety of geometries. Initially we looked at through the thickness cracks, then we moved on to embedded cracks. So, in the case of an embedded elliptical flaw, what do you find? The expression of K is given in this fashion and it varies as a function of theta. What does this imply is, along the boundary of the crack front, the stress intensity factors keeps changing, and you locate the point corresponding to a given theta like this. You put a angle theta, it hits this circle, from there you drop a line and you have this point located on the ellipse. For this point on the ellipse, you get k1 equal to so much and theta is defined like this, and you also have the quantity I2 expressed in this fashion. And what we will now see is, from elliptical flaw, how do we graduate to surface flaws, and this is where we had looked at in the previous class. How do you model the surface cracks? When you have a surface crack, the surface crack can be idealized as a semi elliptical flaw to start with. Suppose I have a corner crack. The corner crack can be idealized as a quarter elliptic. When I have a flaw like this, this could be idealized as the semi elliptical shape, and a corner crack can be idealized as quarter of an ellipse. So, from the elliptical solution, if you modify with simpler arguments, at least for small sized cracks, these results could be comfortably utilized. That is how people have proceeded. When I have a semi elliptical surface crack, you have to remind yourself the notational change. The length on the surface is taken as 2c, that is the major axis of the elliptical flaw is taken as 2c, and the depth inside is taken as a. If I have a full form of it, it will be 2a. It is a semi elliptical flaw we are considering, and you make a neat sketch of this and consider that this is a infinite object with a surface flaw. You make a neat sketch, you have a uniformly distributed stress field, and you have this length as 2c and a, and we all know when we have a semi in a SEN specimen, you have a crack emanating from a free surface. So, what we did, we simply modified that sigma as 1.12 sigma. So, what people have initially have attempted to find the stress intensity factor value is, they have utilized the similar approach. Based on the elliptical solution, you have the expression for the stress intensity factor for a surface flaw given like this: k1 equal to 1.12 times sigma root pi a. This is the only change. You divide by I2 and put this expression in terms of theta, sin squared theta plus a by c whole squared cos squared theta whole power 1 by 4. So, what we have done is whatever the knowledge that we have gained in analyzing SEN specimen, we have extrapolated, combined the result from a embedded elliptical flaw. As we have modeled the surface crack as a semi ellipse, we now say change sigma to 1.12 sigma, and we will again look at similar results like what we had seen in the embedded flaw. The stress intensity factor does not remain constant, but varies on the periphery of the crack front, and we will see on the major axis and at the ends of the minor axis how these values turn out to be. At the extreme end of the minor axis, that is theta equal to 90 degrees, the stress intensity factor is given as K190, that is equal to 1.12 sigma root pi a divided by I2, and this happens to be the maximum value of stress intensity factor on the crack front. And suppose theta equal to 0 degrees, that is at the end of the major axis, the value of stress intensity factor is given as 1.12 times sigma root pi a divided by I2 multiplied by a by c whole power half. You know, this expression is very significant, it carries quite a lot of information. First thing you have to recognize, when you have a surface flaw, stress intensity factor does not remain constant on the crack front, it changes from point to point. So, what does it imply? The crack can have a preferred way of extension. We saw in the case of an elliptical flaw, the elliptical flaw which is embedded would try to become a circular flaw, because that is how the stress intensity factors were varying. So, yes, similar thing also can happen in the case of a surface flaw, and this also helps to appreciate the concept of leak before fracture. You have stress intensity factor higher at this point, so the crack will try to penetrate inside rather than on sideways. The segment of crack tip which is deep inside the material possesses higher stress intensity factor, and in view of this, the crack tends to grow deeper than sideways on the surface. So, when it grows deeper, it is beneficial for us. Only based on such observations, people have also brought in a criterion called leak before break, which is achievable. This is how a material will respond. If you adjust your design parameters suitably, you can ensure that leak always occurs before break. Because it is possible, people have also evolved this as a criterion, and we will see a nice animation which gives you this pictorially. So, what we are actually saying is a crack which is a surface crack like this would proceed in this fashion. You know, whatever the flaw that you have here, it will proceed in such a fashion that it becomes a circle, and you have to note down many things in this. What we want is, if the crack grows like this and touches this surface, if I have a pressure vessel, the pressure vessel would start leaking. When it starts leaking, what you can do? First of all, you can go and find out something is gone wrong and you have to go and correct it. Other way of looking at it is, when the pressure vessel is leaking, automatically the loads acting on it comes down. So, it is also a protection in that, from that point of view. So, when the load acting on it comes down, it is good. However, you could also have crack propagated because of a water hammer. In that case, the pressure would be higher than the original pressure. So, when you are designing, you have to ensure both the possibilities, pressure coming down or pressure going up also. Pressure going up has to be looked at much more carefully. And another aspect also you can learn from this. If you go and look at the literature, we would also discuss about this towards the end of this class. When I have a crack front like this, in the zones which are closer to the front of the crack front here, away from the edges, this is more or less in a plane strain type of situation. You have a triaxiality constraint predominantly present, and you would use K1C as a fracture toughness for this, which is the plane strain fracture toughness. And I had mentioned, without showing a graph, that the fracture toughness is a function of the thickness. In plane stress, fracture toughness is higher, in plane strain, fracture toughness is the least. In the case of a surface flaw, what happens? You have a nice combination, stress intensity factor is higher in this zone of the crack front. Not only this, the fracture toughness that is to be used for propagation of this has to be plane strain fracture toughness, which is usually less than plane stress fracture toughness. Suppose the crack has become fully grown, then you can consider this thickness as idealizing a plane stress situation. When the crack has to move sideways, we would essentially use plane stress fracture toughness, and plane strain fracture toughness less than plane stress. So, you have a good combination that the crack will open up and then touch the other end, then it will start propagating sideways. So, what are the stages in this? See, you need to have a crack developed on the surface, then crack has a growth phase by some growth mechanisms, then it reaches instability. And what when it happens? It penetrates first through the thickness, because your fracture toughness is also lower and also your stress intensity factors are higher. Once it has reached the other surface, it is not that it starts proceeding on sideways immediately. If it proceeds immediately, then you have no hold. In the lay before break criterion, what you want to ensure is you want to have a healthy gap between the crack moving front and then moving sideways. That is why you alter the design parameters in such a manner that you have sufficient time to go and attend on to it. Let us look at this. So, what we want is it has to reach this stage and then allow the fluid to escape. So, you have a possibility to do some kind of a repair or stop the plant, do some corrective measures. On sideways, you will have a growth phase followed by instability. It is not that it becomes unstable and then penetrates through the thickness and move sideways. If that happens one after another immediately, then you do not have that leak before break criterion satisfied. In a leak before break criterion, you try to ensure that you have sufficient margin of time for you to attend on to it, and it is doable. The way you have looked at stress intensity factor variation over the crack front and also the fracture properties, what you find is leak before break criterion, if you really play with the design parameters, is doable. This knowledge you would not have got when we were discussing only the through the thickness crack. In a through the thickness crack, what you saw on the crack front, stress intensity factor remain constant. Once you come to elliptical flaw, you find the stress intensity factor varies on the crack front, and you have a favorable situation in the case of a pressure vessel piping, where you can really achieve leak before break, provided your design is properly checked for. And people also have looked at, suppose I have a shallow crack. In a shallow crack, IT is close to unity and SIF at 90° becomes simply 1.12 sigma root of pi a, and we have already seen that what you have here is because of a free surface. You call this as a back free surface correction, because we are going to see shortly a front free surface correction. Keeping that aspect in mind, you call this as a back free surface correction. Suppose I have a crack front, I can have a front surface as well as a back surface. If I am going to apply only one correction factor, I would say free surface correction factor, because I have a separate correction factor for back free and front face, you call it different. So, one way of making our knowledge in a comparative sense, a shallow crack is equivalent to a through the thickness edge crack of length A. And we have always seen edge crack is more dangerous than a central crack. Not only this, we will also see later, though you compare a surface crack with a through the thickness crack, on the crack front in the through the thickness crack in thin plates you use plane stress only. Whenever you have a surface crack, even in a thin plate, on the crack front, because of triaxiality constraint, you will have to use plane strain fracture toughness, which is lower than that. So, in a sense, a surface crack is always more dangerous than a through the thickness edge crack. That you will have to keep in mind. Though the stress intensity factor is similar, but the fracture toughness we would use differently for a surface crack. And in the next chapter we would discuss in detail how to calculate the plastic zone, and as surface cracks are very important, people thought in what ways you could improve the results that we have obtained for surface cracks. So, people felt when you are applying for ductile materials, it is also desirable to do some correction factor for development of plastic zone, and one of the simplest ways to handle this is, when you have a crack length of A, you take a additional small length which is calculated by a certain procedure, which we would see in the next chapter. We would just look at the result. Instead of using crack length as A, you will use a modified crack length, and that is what is mentioned here. Plastic deformation makes the crack behave as if it is longer than the actual physical size. So, you are going to have what is known as RP star. The rest of the expression is same as what we had seen when we had put this factor 1.12, and the RP star, this is the historical value. This was reported by Irwin in 1960. In the next chapter we would see better estimates of this additional length. So, you must take this more from a historical perspective. So, I have RP star is given as K1 squared divided by 4 pi root 2 multiplied by sigma squared ys, where sigma ys is the yield strength of the material. And I want you to write down this expression. In those days people have only slide rule and things of that nature. So, people always wanted to have whatever the final result in the form of a graph, and we find that people have simplified this, and we would also have a look at it. So, when you write the expression for this additional crack length and simplify, the expression for K1 changes to 1.12 sigma root of pi a divided by square root of I2 squared minus 0.212 sigma squared divided by sigma squared ys whole multiplied by sin squared theta plus a by c whole squared cos squared theta whole power 1 by 4. And this is represented differently for convenience sake, and we are really talking about the maximum stress intensity factor that occurs at the minor axis of the surface flaw, that is given as 1.12 sigma root pi a divided by q, and you have graphs available from which you can get the value of q. And when you are handling ductile materials, you will have to worry what is the applied stress in comparison to the yield strength, that is also a factor. When you are really looking at plastic zone correction, what is the level of stress I have applied to the object in comparison to yield strength also plays a role. If the stresses are closer to yield strength, then the correction factor is having a more influence. If you are operating at a lower stress, then the correction factor has a marginal influence. So that is also becoming one of the important parameters. So in order to evaluate the value of maximum stress intensity factor, people have provided graphs, and these are very popular graphs because surface flaws are so important, and when you look at the literature, you have this as a flaw shape parameter. They have a very characteristic appearance, and on the x axis you have the ratio, you have the value of q. On the y axis, if you look at the crack, the length is given as 2c and the depth within the material is given as a. So a by 2c is plotted on the y axis, and this you do it for different values of sigma by sigma ys. Here it is equal to 1, and I would have graphs drawn for other cases also, and I would like you to make a neat sketch of this. So the flaw shape parameter is very important when you are handling surface flaws. And what you find here, if I remember k equal to sigma root pi a, by putting 1.12 or putting q, you are able to graduate from through the thickness crack, central crack to edge crack, from edge crack to surface crack, all that have similar appearance. We will also have a summary of this at the end of this class if possible, and for shallow surface cracks all this discussion is valid. I would have the graph drawn for other values of sigma by sigma ys, and this is a very characteristic shape of the flaw shape parameter. Even when you look at this kind of a graph, even if it is not labeled, you should be able to identify that this is the graph for flaw shape parameter. So from the graphical approach you can find out q. Sigma is easy to know from the way you have applied the load. So you can find out the stress intensity factor, that is the maximum value for the surface flaw. And I had already mentioned, people also thought once you have the result, how to improve its accuracy. One way of doing it is bring in plastic zone correction. Other aspect is, when I have a crack, you just make a observation of this. Maybe I could enlarge this. I have a crack here, I have the thickness b, this becomes the back free surface and this becomes the front free surface. If the crack is shallow, which is closer to this surface, a back free surface correction is all right. People thought they would analyze initially shallow cracks, but you will also have to look at what happens to cracks which are growing in the thickness direction. So, when they grow, you have an influence of this surface also comes into the picture, that is called a front free surface, and that is given by this simple mk. So, I have 1.12 multiplied by mk sigma root of pi a divided by q. So, this is an improvement over the result what you have got for the surface cracks. So, you have these graphs also available. You have these graphs plotted for a by 2c as well as a by b as a parameter. For different values of a by b, that is different values of the depth of the crack with